Welcome to the Instrument Systems video on ultra-high resolution pixel metrology. Cutting-edge high-resolution OLED and micro-LED displays are similar in that they are comprised of millions of small individual light sources that need to be individually characterized in order for the display to be working at a high level. For correcting defects in this type of display, advanced quality testing is necessary. This can be on the larger scale, looking at the overall uniformity of various properties of the display across the entire surface, or it can go down to the individual pixel level, looking for defective pixels or ones that are on but need some type of correction in terms of their luminance or of their color. If this type of quality testing isn't performed properly, artifacts can be introduced into the process, including Moire or image reconstruction artifacts, and polluting the data being used for correction can lead to some defects still being present. For this type of quality testing, we've developed the LumiTop X150. It combines a very high resolution camera with a pixel shifter, allowing for full screen images of a display where each individual pixel can be resolved, like what's shown on the smartphone display in the lower right. It can do this in one measurement, making it suitable for production applications where takt time is crucial. It can also resolve structures down to 3 micrometers in size, making it perfect for any high-resolution display or wafer. Now, the information in these images needs to be processed in a form that makes it suitable for pixel correction. For this purpose, we've developed fast algorithms to generate pixel intensity maps from the images of the display. Pixel intensity map is shown on the left. It has the same dimensions as the resolution of the device being investigated, and it's a form of lookup table which allows for investigation of the behavior of each individual pixel on the display. When combined with defect detection tools we've developed, it allows for detecting defective pixels on the basis of a number of aspects related to the luminance and color. This type of pixel intensity map serves as the basis for a de Moire process where the behavior of defective pixels can be corrected to make a more uniform display. The behavior of individual pixels varies considerably depending on the brightness level that it is set to. This is particularly true for very dark levels. The images shown on the right show the detailed behavior of individual pixels when the overall brightness of the display is varied. The higher the number, the higher the gray level, and the higher the overall brightness of the display. We see in the upper left, the behavior of individual pixels varies greatly depending on its location on the display and also on its color. And this variation is not comparable to what is seen in the brighter images. This means that for proper de Moire or pixel correction, it's necessary to perform detailed pixel analysis at each gray level that is to be corrected. Defects in the display can also occur on a larger scale. Non-uniformities, like the systematic variation in the color shown on the left, can also be identified and corrected with a pixel intensity map. Artifacts during the capture process complicate pixel correction and must be avoided at all costs. The first is Moire. Moire is a type of artificial pattern in an image that results when a display with a regular pixel structure is investigated by a camera also with a regular pixel structure. The presence of Moire depends upon the ratio of the resolutions of the display and camera. With an ultra-high resolution camera, like in the X150, where each pixel of the display is well resolved, Moire can be avoided completely. A second class of artifacts are related to stitching and splicing of images together. It is possible to make one very high resolution image using multiple images from multiple cameras or from one camera that is physically moved over the device. However, this involves splicing images together, which is a complicated process that needs to take account of different factors, including differing observation angles and different calibrations for each exposure. These additional processing steps introduce error in the pixel correction process and are slow, as they involve considerable image processing and also potentially mechanical movement. This makes them unsuitable for a production application. These artifacts can be avoided by taking one exposure with an ultra-high resolution camera. To recap, cutting-edge OLED and micro-LED displays require analysis and correction on the single pixel level for optimal performance. The combination of a high-resolution camera and pixel shifter in the LumiTop X150 enable one-shot analysis of every display pixel that avoids typical artifacts, and fast algorithms enable processing the image data to a pixel intensity map for fast and straightforward pixel and uniformity correction.